Hey everyone. Today I want to fix an inductor bug, and I'm streaming it because I think there are some interesting things about navigating around the inductor codebase that aren't obvious when you're just looking at the final end product. I'm going to try to show you how I reason about things in Inductor. And I don't count myself as an expert Inductor developer. I just sort of, figure things out as I go. I spend most of my time in other parts of the code base. So unfortunately or fortunately, I already know what the bug in this case is. So I'm just going to sort of replay how I diagnose the bug and how we're going to fix it. Fortunately, because I won't waste time, not knowing what the solution for this bug is. Okay, so what do we got going on here? So here I've got a simple, Torch compiled program. Some things that are interesting about it. We are calling toList on the result of the tensor here. So there's actually some sort of where we're actually going to fetch out the data from the tensor and then return that directly. So this is going to return an integer. All we're doing is we're summing a tensor, we're doing a view on it. The view is actually kind of important to trigger the bug. It doesn't trigger if you don't have the view. And then we're just converting into a list of integers and we're returning this. And so this is going to fail when we run it with Torch Inductor. I've already run it right before the cast, and the error it's failing with is something very obscure. Attribute error, pointwise object has no attribute get name. Seems kind of strange. What the heck is this? Why is it failing in this way? And there's this big backtrace. So how are we going to go about solving a problem like this? Well, let's first take a look at where exactly this is failing. What exactly is this line of code, right? So 6335 get adder. All it's saying is, hey, I'm trying to get an attribute on a mutable box and this thing doesn't exist. Okay, so not that useful, okay? Why are we trying to call getName? Well, we're trying to call getName because we're inside we're inside the scheduler. So the scheduler in Inductor is the thing that after you have generated a bunch of Inductor IR, we're trying to actually go ahead and turn it into a series of Trident kernels, which we're actually going to compile, right? Because not everything can be put into a single Trident kernel. We may end up with multiple fusion groups. And the scheduler is responsible for figuring this out. And so in the course of doing scheduling, one of the things that it needs to do, going to line 129, one of the things it needs to do is it needs to go figure out for any given node what buffers it reads from and what buffers it writes to. So we're just going over here. We're asking the node, what are the read writes of this node? And the read writes of the node are computed simply by, let's just hop over here, 3348. The read writes of the node are computed by simply going through each of the inputs on the kernel and then asking, hey, what are the read writes? And what are the read writes? Well, it's simply the name of the thing in question. So if we just think about, what's going on here a little bit, what's going on here is, we have an input to this inputs kernel, and we want to figure out what buffers it's reading from. So we look at the input, and we see that we are trying to get out what the buffer name of the thing is. And the object we have, which is a pointwise object, does not have a buffer associated with it. So this is the bug, proximally speaking. Okay, so how do we fix this? Well, this seems a bit strange. I don't think I want it seems reasonable for there to be a pointwise object in this situation, right? If we go back to the original code that we were looking at before, we see that there's some reduction going on, and then there's some view going on, and they're converting to a list. So there's actually, I guess the pointwise operation might be the sum in this particular case. But it's kind of strange, right? Like you'd kind of expect this to be fine and to why can't I just have a pointwise to be an input to the kernel in question? So, okay, so that's a little confusing. So how can we get some more information? So one of the really useful things you can do is you can run your program with torch logs. And in this case, I'm asking for debug input from Inductor. And when I do debug input for Inductor, Inductor is going to helpfully give me some more information about what exactly I am compiling. So let's just go ahead and run this again, but with I'm gonna get some. I'm gonna make the log messages a little shorter so that they're easier to fit in this terminal. This is a new feature that I think Oga has added. Pretty cool. Just makes the log messages a little more compact. So we got the same error, and what is it saying? Saying, hey, you know, what are we doing? Well, this is the program we're trying to compile. So what do? I summed up my tensor, and then what I'm doing is I'm selecting out each individual element. So this is what toList turns into. It turns into get me the 0th element, the first element, the second element, and then I'm calling this local scalar dense kernel, which actually goes ahead and gives me the integer in question. And those are the things we're actually going to return in this case. And so we can see that we lower all of these things, and then eventually, oh, well, this is not useful. So we've successfully lowered everything because we've managed to lower the return thing. And now we're at scheduling. And what I was actually hoping was it was going to print me the node in question, but it isn't. So we're just going to ask Inductor to print the node for us directly. So where do we want to put this in? Why don't we do this in scheduler? Scheduler 1311. I'm just going to go ahead and stick a breakpoint here. Inductor in general is a very dynamic code base. There's all sorts of virtual method calls all over. It can be pretty hard to figure out where any given function call goes. So really, backtraces, running the code for real, breakpoints, all your best friend. Like definitely highly recommended. I used to work on a compiler in a language which I didn't have a debugger, and so it took me a while to get used to this mode of operation, but it's really helpful when you are working in Python, because it's so easy to make a change and then go ahead and do it. We're gonna go ahead and do this. All right, so we've hit this breakpoint, and let's take a look at what this node is. All right, cool. So we're trying to create a node for this dynamic scalar call. So I happen to know, because I wrote this logic, that when I do a local scalar dense call, this lowers into its own special IR node called dynamic scalar. In general, when you look at any given A10 operation that you're lowering an inductor, it's going to map to some sort of IR node or multiple IR nodes, as the case may be. And each of those IR nodes, has some logic for how it's implemented. And so what exactly does this say? It says, hey, what is the dynamic scalar? The dynamic scalar takes an input. What is its input? Its input is some sort of tensor. It's actually this tensor box thing. What's inside the tensor box? The tensor box is basically just a container that says, hey, there's a tensor inside here, and it allows us to swap things out depending on what they need. Well, what we have in here is a view of a slice of a storage, which was computed by a pointwise IR node. This pointwise IR node is actually the sum, but what has happened? We've actually unrolled the sum. So all it does, it goes ahead and reads in the 3 elements and then does it directly. That's why it's not a reduction. It's a pointwise kernel because we're actually just reading out 3 arguments one by one. Okay, so what is going on? So remember, our error is that we're trying to get name on an input, in this case the tensor box. And the tensor box does not implement getName. Actually, it does, right? What it does is it says, okay, to get the name of a tensor box, you get the name of the view. To get the name of the view, we ask for the name of the slice view. To get the name of the slice view, we ask the name of the storage box. And to get the name of the storage box, we ask the name of the pointwise. So why doesn't the pointwise have a name? That seems a bit odd. Well, to answer this question, we need to know a little bit about IR in Inductor. Actually, let me delete this breakpoint. So there's a nice comment at the top of the IR doc that Will Constable wrote that I always find myself looking at, which is like, what exactly is the Inductor IR, right? So Inductor's IR produces by executing lowering code, right? So we have a bunch of ATON operators in an FX graph, and then we produce this IR node. And tensor boxes represent torch tensors, right? And so a tensor box will typically point to a storage box, which points to a buffer. And this represents something that where you've actually got an actual tensor. And then there's a bunch of other IR nodes. So Inductor has this big obsession with buffers, right? So buffers are things we've actually materialized. We've actually written them out onto some actual physical storage on your GPU. And, those are the things we expect to be able to get references to. But we also have a lot of constructs in the IR which do not necessarily have materializations in memory, right? Like, for example, if I'm doing a bunch of pointwise operations and, they're just, I'm adding and then multiplying and whatever, I don't actually need to materialize each individual result, right? I don't want to do this because the whole point of Inductor is to let me fuse these into one operations where I never materialize any of the intermediates. So in fact, I only have a buffer in Inductor when I have decided that I absolutely need to materialize it. And when I don't need to materialize things, I'll actually have things like pointwise floating around. If we go back and look at the printout of the IR node here, what we see is actually that we're referencing this thing, but we've never actually materialized the pointwise operation in this case. And so what we need to do, in fact, is if I want to read out a value from a tensor, I need to actually materialize the tensor. And so that means that I haven't materialized it. Okay, so this sounds like there's something wrong with the dynamic scalar IR node. So let's go ahead and pop over there. All right, so what does this look like? So this is the result of a call to local scalar dense. And there's a few things going on here. Let's take a look at the constructor, right? The constructor says, hey, given some symbol, the symbol in this case is actually just the unbacked symbol that we're gonna do some stuff with. And a data tensor, the data tensor is going to be the real input to this extern kernel. So the data tensor is what we're actually going to go ahead and try to read out the value from. So what is going on, right, is we're getting a data node, but it's not materialized. We can actually insert a breakpoint here and check it out, right? So what exactly does the data look like at this point? Hi, Buffet Codes. Thanks for joining the stream. It has been a long time since the last time I streamed. Okay, so what I've got here, so I got my data buffer, and you can see here that it is a tensor box to a storage box, but the storage box is not materialized. I'm expecting some sort of buffer thing. So, okay, how do I materialize this? So there's a method in Torch Inductor called realize. And what realize does is it says, hey, I need this thing to actually be an actual data type. So if I call realize it mutates the IR so that now I have a real computed buffer that represents the data in question, right? So once I've done this, Inductor is always going to materialize this into data. So Buffet asks, is data.realize a PyTorch thing? Yes, it is a PyTorch thing. So data in this case, so we're inside PDB, and data here is a IR node of type tensor box. And all IR nodes, well, not all, do all IR nodes? Most IR nodes implement a realize method. And the realize method just says, hey, I need this to live in actual memory at this point. None of this like, fusion stuff, because like I'm going to repeatedly access it at multiple indices, or I'm going to, go ahead and pass it on to some other function, which in this case, that's what we're doing here. We want to pass it on to an item call. So in PDB, when I say !data.realize, I'm just running the method live. And then, what I've done is I've mutably mutated the IR so that now I actually have a computed buffer. And inside the computed buffer, actually, you can see that it's still just still just the pointwise operation, but it's now this computed buffer. And computed buffers have names, so that seems pretty promising for get name. Let's go ahead and continue and see if that finishes. So we're going to lower a few more times. Actually, let's go ahead and let's insert this directly into the program. So we're going to try realizing data before we go ahead and do this. So does this fix our problem? I'm going to be mad if it actually fixes the problem. Yeah, it's not supposed to fix the problem. Okay, so this is what this is the way I actually did it originally. I was like, okay, so I've got a problem. It's because my thing isn't realized. I happen to know from having read Inductor code before that there's this thing called realize. So why don't I just realize it and then do that? And so we've actually gotten further in the execution here because we finished scheduling and we're now in the scheduler code gen. So the scheduler has finished figuring out where it wants to put all of these things into various pieces. And now we are going to actually generate code for them. And so now it's saying, hey, I don't know how to generate references to Torch Inductor IR views. So we can once again go and peek around to see what it is that we've got, but it's not completely strange, right? What we've got here. Oops, 9. I'd want to know what the let's just break point here. Haha, yes, I don't like being mad. So I haven't rehearsed this. Okay, so what exactly is the node we've got? So we've got a view to a slice view to a storage box to a computed buffer. So specifically what's going on here is, well, what are we trying to do? So cogen reference. What do we think cogen reference means? Well, we're trying to generate some code at this point in time. And actually, let's just pop into this file for a moment to see what exactly this is doing, right? We're trying to generate some code right now. And specifically what we're trying to do is we're trying to write out some Python code that says, generate a reference to the data tensor that's the input, and then call item on it, right? So I took the input and I called cogen reference on it. Seems very reasonable, right? So what the PDB is telling me at this point is it's saying, hey, I don't know how to generate a reference to a view, right? Because that's what view is. Self is a view. Now, if we had, let's see, this data is to a slice view, to a storage box. If I had a storage box, and I call cogen reference to that, I do know how to generate this, right? To reference the storage in question, all I need to do is go ahead and like give you the name of the storage in question, and now I have a reference to it. But if I have a view, right, the view is not the same thing as the storage. The storage is going to be some sort of, in this case, size 4 thing, right? But if I'm doing the view, I might actually need a narrowed version of the tensor, right? Like I can't just bong in buff 0 here. In fact, we can try this patch. So on class view, let's implement cogen reference. And the way we're going to implement it is we're just going to return cogen reference is a method on IR nodes. It says, please give me a piece of code that refers to the IR concept in question. So what if we just implement cogen reference as I need to give it a writer method as just, hey, get the name, right? What will happen when I do this? So you can see we actually generated some code. And then it seg false. Let's look at the generated code for a moment. There's something wrong with my inductor setup right now. It seg faults whenever an error is raised. It's not supposed to do that. It's supposed to just give you an error. Okay, so look what's going on here, right? So we have allocated a buffer. We go ahead and fill it with our elements, and then I'm going ahead and calling item on this buffer. So this is wrong. This is wrong because the buffer is not a 0 element tensor, right? It's 4 elements. So I actually need something like buff 0, 0 to do this. Actually, is this good enough? Let's go ahead and see if we can run this file directly after this edit. Yeah, see? So it actually works if I, do the view correctly. But if I don't do the view correctly, then I think this is going to seg fault. CUDA initialization, so slow. There's a question in chat, which is, what's the original code that you're trying to generate the IR code for? That's right. Yeah, see, it's seg faulted. So we can just pop up earlier in our logs to take a look. And so we do a sum, giving us a size 4 tensor. And then I want to select out the 0th element of this 4 element tensor and then call item on it, local scalar dense. And then I do that again for element 1, 2, and 3. So like, this is very strange, right? So it miscompiled only the first one. The second one's got this reinterpret tensor call, but the first one somehow skipped out on reinterpret tensor to be a scalar tensor at offset 0. So seems very questionable. So we could try to solve this by going further and trying to re-implement this missing functionality. But actually I got some help at this point. So the help I got was this. I was thinking about, surely this is something that people have wanted to do before, right? Like if I've got a view to a tensor and I want to pass it to an external kernel, we've got plenty of external kernels in PyTorch. Anything that Inductor doesn't know how to code gen, we just go ahead and call the A10 implementation. So there's plenty of situations where this happens. This is not broken in reality, right? So there must be some code that is doing this correctly. So what is that code? Well, let's take a look at extern kernel, because extern kernel is typically what we call when we go ahead and have a call to external kernel. And in fact, let's look at a specific subclass of it, extern kernel alloc. So extern kernel alloc is a subclass of extern kernel, and it specifically refers to when I am an inductor and I want to call a function that is going to allocate the result for me, versus other in-place functions where I pass in all the arguments and then it just goes ahead and modify it. Let's take a look at the initialization function for this. So an extern kernel alloc takes some number of inputs and then calls a superconstructor with, what's this? We're not passing in inputs directly, which is what I did here. All right, here I just pass in data on its own. I'm calling this unwrapped storage method on it. So let's just take a quick look at what unwrapped storage does. So unwrapped storage says, well, for each of the inputs, go ahead and unwrap storage for input. And what does unwrap storage for input do? It says, well, if it is a tensor box, just give me whatever is on the inside. And then if I have a base view that's not a reinterpret view, I need to realize the input. What do you think realizing the input does? Well, to realize an input, if I have a view, I have to realize the view, and then I have to convert it into a reinterpret view. So this actually is exactly what we needed to do, right? We need to realize on the thing to actually, put it in a buffer somewhere. And then this apparently says, hey, we don't code-gen views. We just code-gen reinterpret views. So, okay, cool. So we just need to fix this by saying self.unwrappedStorage data. And so let's see if this works. Hooray! It worked! And our bug is fixed. So turns out to be a one-line change. So let's go ahead and put this into the test suite. So I need to decide what test file I'm going to put it in. Let's go ahead and put it in test torch inductor dynamic shapes, because usually things involving this sort of thing go here. Let's go ahead and pop it over. I just like to find a random spot. Okay, test item materialize. Let's paste this in. You don't want to actually modify this directly, but we have a nice decorator that lets you temporarily patch stuff. So I just want this decorator, and it's capture scalar outputs. And it's pretty common to not compile the thing directly, but do it out of line, so you can have the compiled function and the non-compiled function all together. So then we can just say, hey, the compiled function's output should equal the regular function's output. And let's just check that our test works. And then we can send it in. Okay, so what have we learned today? So I fixed a simple bug in the IR construction where I wasn't properly unwrapping storage before passing things on to external kernel. To fix this, we had to understand a little bit about the internal universe of buffers versus computation, like pointwise, inside Inductor, right? Inductor has a notion of computation, but when it actually wants to materialize something, it turns it into a buffer. So when you are writing lower rings in Inductor and you need to materialize something, you need to call realize, or in this particular case, when I actually want to send it to an external kernel, I need to unwrap the storage to actually get it into a form where I can generate the reference to it. We also looked at some meta strategies for working with Inductor codebase. For example, I used breakpoints liberally. I looked at the stack trace. I looked at the logging. All of these things are useful for figuring out how things should go. I also thought to myself, hey, this thing that I want to do, I think the compiler should be doing it somewhere else. And I found where it was doing it somewhere else. And that was how I figured out how I should actually go about doing these things. So yeah, so that's everything I wanted to cover today. Any more questions from the stream readers? Buffet codes? Y'all good? All right. Thanks, everyone. See you all next time.